November 19, paper 6, variant 3. Question 1. A student investigates how the resistance of a filament lamp changes with the potential difference across it. Okay? On figure 1.1, draw the symbol for a voltmeter connected to measure the potential difference across the lamp. Can I draw the potential difference? Can I draw the voltmeter to measure the potential difference across the lamp? So you have a voltmeter across the lamp. That's it. Voltmeter across the lamp. He connects the crocodile clip at a length of 20 centimeters, the length L, 20 centimeters. He records the voltage V and the current I. The voltage V would be 0.6, okay? 0.6 volts. Okay, and I would be 0.14, 0.14 amps. Okay, now the voltmeter, voltage, and the current. Now, can I find the resistance? R equals 0 over I. Yes, I can find the resistance. R equals 0 over I. So 0.6 divided by 0.14. Okay, 0.6 divided by 0.14, which is very close to 4.3. 4.3 ohms. Now, we need to plot the graph of R on the y-axis, R on the y-axis, and L on the x-axis. L on the x-axis. The L is quite easy. 20, 40, 60, 80, 100. Can I start at 0? Yes, I can start at 0. 20, 40, 60, 80, 100. If you want to start with 20, it's okay. 20, 40, 60, 80, 100. What about the resistance? It's all the way up to 13. Starts with 4. 4, 6. Can I start with 4? Let's see if I can start with 4. So if I say 4, 6, 8, 10, 12, 14, would that be enough? Yes, it would be enough. Okay? It would be enough. Huh. Okay. Now, can I plot the points? Yes, 20 and 4.3. 4 point, how did I get 4.3? 0.6 divided by 0.14. 20 and 4.3, where is 4.3? So this is 5. 4.3 would be square and a half above 4. Okay, right over here. And then 40 with 7.5. 40 with 7.5. So this is 7.5. 60 and 10. 60 and 10. 80 and 12. And then 113. You have a graph, okay? Last point is, what is 10 and 13? Is this a straight line? Can this be a straight line? No, this is not a straight line. This is a curve. This is definitely a curve. One of the very few questions when you are required to draw a curve, which is okay. I'm okay with that. Can I draw a curve? Yes, I can draw a curve. Okay. Drawing the curve using your hands. Do not use the ruler while drawing the curve. Straight, not straight. It's a smooth curve. A smooth curve. Smooth curve, just joining all of the lines, all of the points. Now, student notices that the lamp is very dim when the length was 20 centimeters, but becomes very bright when the length is 100 centimeters. It's very dim, very dim when the length was 20 centimeters, but then becomes very bright when the length is 100 centimeters. State what the shape of the graph tells you about how the resistance of the lamp changes when the temperature of the filament lamp, or with the temperature of the filament lamp. Justify your statement. If we take a look at the graph, okay, if we take a look at the graph, as the resistance increases, okay, he said that the lamp becomes what? The lamp becomes more brighter, right? The lamp becomes more brighter. And this is due to the, not just increasing the voltage or what, this is due to the increasing the temperature of the lamp. It's due to what? Increasing the temperature of the lamp, because he left the lamp on for quite a while. So when you increase the temperature of the lamp, the resistance increases. Increase the temperature of the lamp, the resistance increases. So the statement here would be, as the temperature increases, the resistance of the wire, or the resistance of the lamp, increases. As the temperature increases, the resistance of the lamp increases as well. Justification. The justification, the temperature of the lamp. Okay, the temperature of the lamp itself. The lamp itself gets hotter because of the resistance, because of the current passing through the coil inside it. Okay, um, just justification would be that the resistance increases with the length. Yes, the resistance increases with the length or the temperature as well. Okay, the temperature and resistance. Let's just write down resistance instead of writing down temperature. The resistance increases, okay, with the length. That's why the lamp keeps on getting brighter. If you leave the lamp on for a very long time, it will keep on getting brighter. Why will it keep on getting brighter? Because of the temperature of this lamp. Okay, when the temperature increases, the lamp keeps on getting brighter and brighter. Hmm. Okay, in this experiment, it is possible to change the current using a variable resistor. Using a variable resistor. On figure 1.3, complete the diagram to show a variable resistor. Okay, to show a, can I just draw a variable resistor? Yes, I can draw a variable resistor. For example, if you want to draw the variable resistor in this point, this is the variable resistor. What about the remaining graph? What should I do? I should just complete it this way. Okay, that's all you need to do. Just draw the remaining graph. That's all you need to do in this question. Hmm. Moving on, moving on. Yeah. Soon sees that the distance u between the illuminated object and the lens. Okay, she sets the distance. She moves the screen on figure 2.1. Measure the distance u and v. Can I measure u and can I measure v using my ruler? Yes, u and v. U should be 5 centimeters. Okay, 5 or 5.0 centimeters. If your reading is slightly less than 5 centimeters, it is okay. Measure the distance v between the lens and the screen. Distance v would be 7.6 centimeters. Again, if your reading is slightly less, it is okay. Okay, figure 2.1 is drawn 1/5 the scale. Can I find the actual distance u and the actual distance v? Yes, just by multiplying by 5, because it's 1/5 the scale. So 5 times 5, 25 centimeters. 7.6 times 5, 38 centimeters. Can I find F1? Yes, I can find F1. UV over U plus V, right? UV, capital U, not small u. So 25 times 38 over 25 plus 38. Okay, can I find F? Yes. It would be 15 centimeters. Okay, okay, again, not too bad. Briefly describe a technique to obtain an image on the screen that is as sharp as possible in this experiment. Technique to obtain an image on the screen that is as sharp as possible. How can I produce a sharp image on the screen? One of the precautions we are used to while dealing with this experiment, move the screen slowly, okay, back and forth. Move the screen, okay, slowly back and forth. On figure 2.2, measure height h0 of the illuminated triangle and then the height of the image. Okay, can I measure 2.2 and 2.3? Yes, HO would be 1.5 centimeters. If you're reading a slightly less, it's okay. HI would be 2.4. Again, if you're reading a slightly less, it is okay. Can I find the magnification? HI over HO. Yes, 2.4 divided by 1.5. Right? 2.4 over 1.5, which is 1.6. Should I write down a unit? No, you cannot write down a unit. This would be completely wrong. Why? Because this is a magnification factor. Okay. It's a ratio, for example. It's a ratio. So there's no unit. You cannot use a unit in this ratio. Can I find the second value, f2, for the focal length, using v over m plus 1? What was v? Value from AII. Where is AII? Ah, AII. So v is 38. Okay, v was 38 divided by 1.6 plus 1. Can I use it? Yes. So f2 would be, yes, 14.6, or you can write down 15 if you want two significant figures, right? Centimeters. Yes, you have to use the unit. Centimeters. Are F1 and F2 equal? Yes, they are equal. Even if you wrote down F2 to be 14.6, again, it would be still equal to 15, which was F1. Yes, they are equal. Yes, they are equal. You have to say that the values, okay, are close and within, okay, the limits of experimental accuracy. Of experimental accuracy. Hmm. State one precaution that could be taken to ensure the measurements of this experiment are taken as reliably as possible. Uh, one of the precautions we say, one of the precautions we have memorized for this type of experiment is to make sure that the object, screen, and lens are perpendicular to the surface. Okay, the object, lens, and screen are perpendicular on a horizontal surface. Someone might say, can I take the reading perpendicularly? Yes, you can take the reading perpendicularly. Okay. Suggest which method, one or two, is likely to give a more accurate value for the focal length. We found the focal length twice, f1 and f2, and he's asking which method is more accurate. Which method might have some problems with it. Okay. Which method might have some problems with it. For me, okay, my point of view, in my point of view, method two might be a bit more accurate. Why would method two be a bit more accurate? Because in method one, measuring the length U and V might be a bit more difficult. Okay, measuring the length U and V might be a bit more difficult. So in my point of view, method 2 is more accurate. If you want to say method 1 is more accurate, you could say so. You could say so. But for example, you might say, well, method 1 is more accurate because, for example, taking the length of the image or the height of the image would be a bit difficult. Taking the height of the image from the screen might be a bit more difficult. So either case, it is correct, but you have to write down the correct justification. Why is this method more accurate? Okay, so if I say method 2 is more accurate, I need to say, well, because okay, method 2 is more accurate. Why? Because taking the readings of V and U is more difficult. Okay. Hmm. Now, can I say D take a reading perpendicularly to avoid parallax error? Yes, indeed, you can say so. Yes. Hmm. Question 3. You have a clamp and a spring. The stretch length L of the spring is indicated in 3.1 and is to be measured. Describe two precautions that could be taken when measuring the length of the stationary spring. What are two precautions that you have to take them? Take the reading perpendicularly to avoid parallax error. Take the reading perpendicularly to avoid parallax error. And then we need to put the ruler close to the spring. Okay, the ruler has to be close to the spring. Okay. Student measures the length L node of the spring without any load. Without any load. Various loads are hung from the spring. The stretched length L on the spring, each load is recorded as shown. So you have L node, which is the length, the origin length, right? 2.1. Origin length is 2.1. And then you keep on adding loads. 1, 2, and 3. The length keeps on increasing. Can I find the extension of each of these lengths? Yes. 6.3 minus 2.1, the original length, is 4.2, right? 4.2. And then 10.5 minus 2.1, 8.3, right? And then 14.7 minus 2.1, which is 12.6. We found the extensions, the various extensions. 8.4, yes, I'm sorry, it's not 8.3. 8.4, yes, thank you. Loads are removed and an object X is suspended from the string. So we removed these loads and we added a different object, object X. We do not know the weight of this object, do not know the load. Measure the stretched length Lx of the spring. Can I find Lx? Yes, using my ruler. I will measure this distance Lx, which should be around 18.4, I'm sorry, 11.4 centimeters. Again, if your reading is slightly smaller, it is okay. So now we have the extended length due to this unknown object X. Estimate the weight of object X. How can I estimate the weight of object X? Well, I have the length to be 11.4. Okay, I have the length to be 11.4 centimeters. If your length is 11.2, okay. How can I find the weight? To be using a proportion. Okay, you need to use a ratio, a ratio. But can you use, that's the question, can I use the ratio of the length to the weight or the length to the force? Is that even possible? Can you even think about doing that? No, you cannot do that. You can never do that. What can you do? What is the only thing that you can do is the extension with the force. You have to write down the extension with the load or the extension with the force. So if I take two numbers from the initial table, okay, the extension, for example, was 8.4 and the load was 2 newtons. The extension was 8.4, right? And the load was 2 newtons. What is the extension? This question, it's 11.4. This is the length. What is the extension? So the extension is actually 11.4 minus 2.1, right? Wasn't the initial length, the original length, wasn't it 2.1? Yes, it was 2.1. So 11.4 minus 2.1, this is 9.3. So if the extension is 9.3, can I find the load? Yes, I can find the load by cross multiplying. 9.3 times 2 divided by 8.4, this would be 2.2. So the load, okay, this estimate for the load would be around 2.2 newtons. Can I use the length? No, you cannot use the length. If you use the length, it will give you a different value, a very wrong value for the load. Length and force are not directly proportional. Length and force are not directly proportional. We only say that the length and the load and the extension, the force and the extension are directly proportional. You cannot include the length while cross multiplying. You cannot include the length while cross multiplying. Explain how you obtained your answer. You can write down that 11.4 minus 2.1 is 9.3 centimeters. So this is the extension, right? This is the extension. It's 9.3 centimeters. And then you can write down the ratio, which we wrote down up here. So you can say 8.4. Okay. You can write down 8.4 to 2 would be equal to 9.3 to 2.2. You can write it down as it is. Okay, again, you have to use the extension. You can never use the actual length. Okay, a student measures the weight of a different load using a smaller method. It's a similar method, right? He gives the weight as 4.532 newtons. Explain why this is not a suitable number of significant figures. Why isn't this a suitable number for? Because we are used to how many significant figures? Only two or three, right? We okay. We only use two or three significant figures. Only two or three significant figures. We never use four significant figures. Very rarely do we ever find, for example, a table or something written down in four significant figures. Another student suggests that E is directly proportional to L. E is directly proportional to L. State whether the results support her suggestion or not. What is L? What is L? L is not the length. Take care. L is not, this capital L is not the length. Check the table. Check the table. This capital L is the force or the load, right? This is the load. It's not the length. Length is the small L. Just take care. Take care. So is L or are L and E direct proportion? I think so, yes. How can I make sure? By dividing. By dividing. So if you say, for example, 4.2 divided by 1, would it be equal to 8.4 divided by 2? Yes. Would it be equal to 12.6 divided by 3? Yes. Okay? Yes. So the statement, yes, they are proportional. Yes, directly. Okay? That's directly proportion. Why? Because you can use these values. 4.2 divided by 1 is equal to 4.2. right? And then 8.4 divided by 2 is equal to, again, 4.2. And then 12.6 divided by 3 is also equal to 4.2. Okay? Okay. Force increases as the extension decreases. This is not the justification for this question. For this question, when he says justify, okay, or use results from the table, then you have to write down results from the table. It's a must. When he says justify using results from your table, then you must use the results from the table. Okay. The difference between directly proportional and proportional is that directly proportional would usually start from zero. As force increases, extension increases. Yes, but again, you need to use the justification. The student wishes to plot a graph L against E to test if the two quantities are directly proportional. Here, in this point, this part is where we say, how can I determine whether this graph is directly proportional or not? By two things from the graph. First of all, you have to say that the graph starts from the origin, okay? Starts from, okay, the origin, and that the graph is a straight line. Okay, two things that determine whether this graph is a direct proportion graph or not. Hmm. Okay, a student is investigating EII. Hmm. If you want to plot the graph of the load against the extension graph, how can I know if this graph is directly proportional or not? When you plot the graph, if this graph starts from the origin, then it is a direct proportional graph. And if it's a straight line, if both if both conditions are satisfied, then this would be a directly proportional graph. If one of these conditions isn't satisfied, then it's not a directly proportional graph. Hmm. Last question. Plan an experiment which will enable him to compare the effects of lids on of different thicknesses. So you have several lids. Okay, you have containers with hot liquids in them, and then you will keep on changing the thickness of the lid, right? The thickness of the lid. Okay. Will this thickness of the lid, will it change the rate of cooling or not? Okay. Will it change the rate of cooling or not? So can I say uh, my range of values, the thing that I'm changing, the independent variable, the range of values. Yes, I need the thickness of the lid. Okay, the thickness of the lid. And can I say 1 centimeter, 2 centimeters, 3, 4, and 5 centimeters? Yes, you can say so. So these are the range of values, the independent variable, the thing that you are changing in this question. Hmm. What apparatuses do I need? So he hasn't given me any apparatuses at all, right? He hasn't given me any apparatuses at all. I need a beaker, right? I need some hot water. I need a thermometer. I need a stopwatch. He hasn't written down any apparatuses at all, right? So for the apparatuses, you need a beaker, you need hot water, thermometer, you need stopwatch, right? You actually need the lid. You need different lids, okay? Different lids with the same material, the same material, okay? Hmm. Do I need a ruler? Yes, you can use a ruler to measure the thickness of the lids. Okay, a ruler. Hmm. What about the... So we wrote down the apparatuses. What are the key variables? What are the constants? Controlled variables. Yes, we have a lot of controlled variables in this question. Hmm. Controlled, okay, variables. What are the controlled variables for this question? You can say the initial temperature of the water, right? Initial temperature of hot water. Okay. The time taken for the experiment, or the volume, first of all, the volume of the water, right? The volume of the water. The time taken. Time taken. Can someone say the room temperature? Yes, the room temperature. Definitely, it is okay. Okay. Same initial temperature, same volume of the water, same material of the lid. We wrote it down. Same material of the lid. Okay. Same room temperature. Okay. Key variables. How will I carry out the experiment? Drawing a table. Okay, you may draw a diagram. That's if you want. I don't really care about drawing a diagram. What are the steps taken? Pour the same volume of water. Okay, the same volume of hot water with the same initial temperature, with the same initial temperature in a beaker. Cover it with a lid. With a lid. Leave the water for a fixed amount of time, right? For a fixed amount of time. When you leave it for a fixed amount of time, or take the reading of the final temperature, take the reading of the final temperature. That's it. That's all you need. That's all you need to do. And then repeat for different lids, right? Repeat for different lid thicknesses. Lid. Okay. These are the steps. Can I draw a table? Yes, you can draw the table. If you want to draw it on these lines, it's okay. If you want to draw it in the empty space above, it is also okay. What are the columns we need in this table? First of all, you need the thickness in centimeters, right? You need the initial temperature, which is constant, I know. Initial temperature, which is constant. And you need the time taken, which is also constant. Time taken in seconds. And the final temperature, which would change. Yes, it would definitely change. And last but not least, we need to write down a simple conclusion. For each thickness, of lids, repeat the experiment. Repeat the experiment and take average. Okay, repeat the experiment, take average. Record the readings in the table. Okay, record the readings in the table. Compare the results. Compare the results by drawing a graph, by plotting a graph, okay, of the thickness, okay, and final temperature, okay, of thickness and temperature. Okay.